Every year, the world's military powers invest billions in developing weapons that are more accurate, more powerful, and more advanced. But among them all, there is one that stands out for its size, surgical precision, and devastating force. It is the GBU-57, known as the Massive Ordnance Penetrator, or simply MOP. Imagine a weapon so heavy that only one aircraft in the world can carry it, so precise that it can hit a target the size of a tennis ball from over 15 kilometers high, and so strong that it can drill through up to 60 meters of solid rock before it explodes. But how is such a bomb built? Today, on Inside the Process, we take you into the heart of the operation to discover how this superweapon is made. Step by step, you will follow the path that turns steel, precision electronics, and extreme aerodynamic design into one of the most feared projectiles on the planet. In the early 21st century, engineers faced a challenge that seemed impossible: to create a bomb capable of penetrating the most fortified structures on Earth, designed to resist any kind of attack. In 2004, Boeing, in collaboration with the United States Air Force, began developing the GBU-57. This bomb not only had to be powerful, but also smart and accurate. Before it existed, conventional bombs could not match the new generation of underground fortifications. In less than 4 years, the project moved from paper concepts to real testing in underground tunnels, a technological leap that redefined what a bomb could do. But the real challenge was not just in designing it, but in building it. Each GBU-57 is an industrial puzzle where a single mistake, no matter how small, could ruin years of work. So how is a bunker buster bomb made? It all starts with the material that gives it its legendary strength: Eglin steel, a special alloy so tough it can withstand impacts that would destroy any other metal. This steel is not found just anywhere. It is made in high-tech foundries in the United States. The process begins with high-purity iron ore, mixed with nickel, chromium, and other elements in exact proportions. In electric arc furnaces that reach 1600 degrees Celsius, the ore turns into a stream of molten metal, glowing like lava. This liquid is carefully poured into giant molds, designed with tolerances so strict that they do not allow even the slightest air bubble or impurity. Why so much obsession? Because a single microscopic crack could cause the bomb to shatter on impact at supersonic speed. Once solidified, the ingots, each weighing several tons, are transported under strict security to a specialized plant in Oklahoma. Before moving them, each ingot is inspected with X-ray scanners and ultrasound to detect invisible flaws. If one fails, it is recycled. There is no room for error. At the plant, the steel enters the first transformation stage: massive hydraulic presses capable of applying 15,000 tons of pressure. Flatten the ingots to give them an initial conical shape, the skeleton of the future GBU-57 casing. This process is so intense that it generates enough residual heat to melt plastic from meters away. But here comes the first obstacle. The steel must cool slowly for days in controlled chambers to avoid internal stress. If cooled too quickly, the metal would become brittle, useless for a bomb that must withstand extreme impact. The casing of the GBU-57 is the core of its penetrating power. At the plant, the steel blocks go through a line of precision lathes controlled by state-of-the-art computers. These lathes, equipped with industrial diamond tools, cut the steel with micron-level precision less than the thickness of a human hair. The tip of the casing, often reinforced with tungsten to maximize penetration power, is shaped into an aerodynamic cone that reduces resistance when going through hard materials like rock or concrete. This step is so critical that a misalignment of just 1/1000th of a millimeter could cause the bomb to veer off course on impact, failing its mission. To guarantee perfection, each shell goes through an ultrasonic scanner that detects cracks or invisible imperfections. If a defect is found, the piece is discarded without exceptions. Then, laser-guided robots polish the surface to eliminate any roughness, ensuring the bomb can slide through solid materials without unnecessary friction. But here is the surprising detail. Each shell is tested in impact simulators that replicate the force of a fall at 1,000 kilometers per hour. These tests evaluate not only strength, but also shape, because the aerodynamics of the GBU-57 are just as crucial as its brute force. Only the shells that pass these tests move on to the next step, a process that can take weeks for a single unit. Now comes the most dangerous moment, filling the shell with 2,400 kilograms of high-power explosive, such as the AFX-757, a polymer-bonded compound capable of generating a controlled detonation with devastating force. This process takes place in a sealed chamber, where operators wearing protective suits work under strict safety protocols. The chemicals that make up the explosive are mixed in refrigerated tanks at temperatures close to -10 degrees Celsius, because even a slight increase in temperature could trigger a catastrophic reaction. The explosive is injected into the shell through a robotic system that controls every milliliter. Here, precision is absolute. If an air bubble remains in the explosive, the detonation could become unstable, reducing its effectiveness or even causing total failure. Density sensors monitor the process in real time, and the data is analysed by computers that alert to any anomaly. To give you an idea of the scale, filling a single shell can take up to 12 hours, and each step is supervised by engineers who review the data second by second. A mistake here would not only ruin the bomb, but could also endanger the entire plant. A process so delicate it seems more like science than industry. The GBU-57 is not just a powerful bomb, it is a smart bomb. In a clean room where the air is filtered to remove every last dust particle, engineers assemble the GPS guidance system, an electronic brain that guides the bomb to its target with an error margin of less than 3 meters, even after passing through dozens of meters of solid material. The circuits are mounted on reinforced boards, encapsulated in epoxy resins that protect them from vibration and impact. This system must survive a fall at supersonic speed, something few electronic devices can achieve. Then come the grid fins, made from titanium alloys that are lightweight yet incredibly strong. These fins, unlike traditional ones, have a mesh design that provides flight stability even at extreme speeds. But the most fascinating component is the Smart Fuse LPSF, which detects underground cavities and delays detonation until the optimal moment. This small device, no bigger than a golf ball, is assembled by hand by specialized technicians because its programming is so complex that no machine can match human precision. Each fuse is tested in simulators that recreate the conditions of a real impact, ensuring that it performs flawlessly under pressure. Before it is considered complete, each GBU-57 goes through a series of rigorous tests. In simulation chambers, it is exposed to vibrations equivalent to a flight in a B-2 Spirit bomber, temperatures ranging from -40 to 60 degrees Celsius and simulated drops. These tests ensure the bomb can withstand the extreme conditions of real use. Then, an anti-corrosion coating is applied to protect the steel from humidity during storage, a crucial detail for a bomb that may sit idle for years. Finally, each unit is packed into a reinforced container designed to endure transport to military bases without sustaining damage. What began as a block of metal is now a masterpiece of engineering, ready for its purpose. On the final assembly line, the bombs are lined up like giants of steel, each one a testament to human precision. Specialized technicians connect the guidance systems and the fuses, making sure each component is perfectly integrated. The process ends with a final inspection, where optical scanners and tactile sensors verify that there are no visible or internal defects. Each GBU-57, weighing 13,600 kilograms, is a colossus that combines brute force with advanced technology. From a molten steel block to a machine capable of changing the outcome of a mission, the result is a piece of engineering that seems to defy the laws of physics. So how does the GBU-57 actually work? Dropped from 15 kilometers in the air, it falls at supersonic speed, guided by a GPS system that directs it with pinpoint accuracy. Its steel and tungsten tip pierces through rock or concrete as if it were paper, while the smart fuse waits for the exact moment to detonate, unleashing an explosion capable of collapsing underground structures. Building a single GBU-57 takes months of work, thousands of engineering hours, and a level of precision that borders on the impossible. Only a few are produced each year, but each one is a monument to what human technology can achieve. From a pile of raw ore to a bomb that redefines the limits of engineering, this is how the Massive Ordnance Penetrator is made. If you enjoyed this journey, there are many more processes waiting to be discovered here at InsideOut. Below, you will find videos showing how everyday products are made. Subscribe, leave a like, and we'll see you in the next video.